Welcome back. In this video we will discuss the simulation of gas networks. In this session we will explain what type of parameters, components and unknowns are required to have a good gas network simulation. Moreover, we will discuss how gas and electricity can be coupled and have an integrated energy network. First of all, let us figure out what the unknowns are in a gas network. An important unknown is the velocity of the gas. This variable indicates how fast gas goes from the beginning to the end of the pipe. This is comparable to the current density in electrical circuits. Another important parameter is the pressure, or, more specific, the pressure difference. For instance, if you have a high pressure difference, the resulting velocity will be high, and if the velocity will be low if you have a low pressure difference. This is similar to the voltage in an electrical circuit. Finally, we have the temperature. It is important to keep in mind that there is a coupling between the parameters. The pressure can be coupled with temperature, and the velocity can also be connected with temperature. Hence, it is required to use different quantities in gas simulation. There are different types of gases available. Let us analyze a few based on their calorific value and density. The calorific value indicates how much heat is produced when you burn it. For natural gas, the numbers are given here. Then we have Groningen gas, which is slightly different, and we have Russian gas, which is again distinct, and finally we have hydrogen gas. As you can see, hydrogen is much lighter but stores the least amount of energy. To use these gases in a house, a city or an industry, we must remember that most burners or furnaces are based on specific calorific values. If the calorific value of the supplies gas differs, we have to mix it, for instance, with nitrogen to get it back to the original value. The mixing should be accounted for in the simulation as well. So, how do we simulate gas transport? If we start with the best mathematical model, we will end up with the Navier-Stokes equation. This provides an accurate solution, but is very complicated to solve, especially for massive networks. For instance, the Navier-Stokes equations cannot solve the gas network of the entire Netherlands. What appears to be sufficient is the 1D equation. The Navier-Stokes equations is in x, y, z directions, the three spatial directions and time. If you have only an equation in the length of the pipe and time, it is already sufficient to have an excellent approximation. This means that we do not have a complete description of the pipeline, but this is sufficient for most applications, except if we have to zoom in for details. So, what components do we need to keep in our model? Firstly, the pipeline resistance. This depends on the material that a pipe is made of. It is measured by how much resistance the gases experience when coming from one end to the other. Secondly, the pipeline connection is a crucial component to model. Here you can see the connection between three different pipes. Things can become difficult here, but in general, we don't use the Navier-Stokes equations. We see it as a sort of a hub and apply the conservation property, which states that what's coming in is equal what's going out. This is generally sufficient for this type of modeling. Finally, we should model the compressors, which are very important to transport gas. A pressure difference is needed to transport gas. To make the pressure difference, we need to include compressors. They are more complicated to describe. In general, we don't describe them in much detail, but we treat it like a black box. Another complication is that they should be powered. This can be done using electricity or gas. In the latter case, gas comes in, drives the machine, and then increases the gas pressure to a higher value to obtain a high pressure difference. Although similar in many ways, there are also some fundamental differences between gas and electricity. Let's have a look at them. In general, gas is much slower than electricity. Electricity can flow in microseconds from one part of the Netherlands to the other. But for instance, if gas is transported from Groningen to Rotterdam, it may take half an hour before it reaches Rotterdam. Moreover, gas is more dangerous than electricity. If something goes wrong in the electricity grid, it is a local phenomenon in general. For example, a short circuit is obviously dangerous, but its impact is limited, because it can quickly be isolated. With gas, this is more complicated. If there is a lot of gas leaking and a spark occurs, you get an explosion that can erase part of the city. So, we could say that gas is more dangerous when compared to electricity. Finally, let's look at storage opportunities. To store electricity is difficult, but storing gas is relatively easy. We can store gas in two ways. The first is to preserve energy in the pipelines. If you increase the pressure, more gas will be present in the pipeline, which can act as a buffer. The second way is to have the surplus of energy generation, for instance by excess wind, transformed into a gas like hydrogen. That gas can then be stored and reused in the future when there is excessive demand. This last property makes it even more attractive to couple the gas and the electricity infrastructure. There are multiple ways the gas infrastructure is coupled to the electrical network. The first one is that to transport both means in parallel. Then we can choose between electricity or gas. Secondly, as I already mentioned, we can use compressors in the transportation line. Electricity can be used to drive the compressor, which leads to gas propagation. Thirdly, gas can be converted in electricity using steam turbines. This is done in furnaces. Another method of coupling gas and electricity is the so-called power-to-gas method. You can see that electricity is used to produce hydrogen that is stored in a container. Then, when needed, the gas can be used to produce electricity. So, there is coupling from power to gas and also from gas to power. The final method for coupling is the combined heat and power plants. Here you can see that all three sources of energy are present: electricity, gas and heat. In this example, we start with gas, feed it to the CHP system, which can then produce both electricity and hot water. To combine different forms of energy, we use energy hubs, which are black boxes. Here you see such a black box, where on the left-hand side electricity can go in and out. On the right-hand side, gas can enter and leave. To model this, we have to include specific conservation laws. What happens inside the box is not essential when simulating. It's only important how much is lost in the transformation. So if you go from electricity to gas, you lose something, which also holds the other way around. There is a certain efficiency involved. It can be 90% or 95%, but you always lose something, which should be kept in mind and in your model. This energy hub can be helpful in two ways. First of all, we don't have to make a detailed model of this energy hub. Instead, we only treat it as a black box. Second, the interaction between the different energy networks can be simplified, making the integration more straightforward. To recap, we have shown what is needed to simulate gas networks. This includes velocity, pressure, and temperature as unknowns, and the resistance, connection points, and compressors as elements. Then we have made a comparison between gas and electricity. Gas is slower, more dangerous, and has higher storage potential. Finally, we discuss how gas and electricity networks can be combined. There are different possible forms: transporting them in parallel, using compressors, generating electricity with steam turbines, and through power-to-gas technology. I'm going to blow off some steam and see you in the following video.